The C language was created around 1972 by Ken Thompson and Dennis Ritchie, who at the time were working at Bell Labs. More accurately, Ritchie created C alone, but Thompson created C's direct predecessor, the B language. In the same time frame, Thompson and Ritchie together created the original Unix operating system, the bulk of which was written in C. Aside from being very widely used, C has also been extremely influential in other languages. The C++ and Objective-C languages, for example, created in the 1980s, extended C with object-oriented features. Because of C's success, the American National Standards Institute, ANSI, codified a standard for the C language in 1989 called C89. This was followed by revised standards in 1990, 1999, and 2011. All the popular C compilers support at least C89, but full support for later revisions is still spotty. The most popular C compilers in use today are the GNU compiler, Apple's Clang compiler, and Microsoft's Visual Studio compiler. Unlike the GNU and Clang compilers, the Microsoft compiler is not open source, but it is free for download. The C language is imperative and procedural, so unlike a functional language, C makes no effort to constrain the use of mutable state, and unlike an object-oriented language, C provides no explicit facilities for encapsulation, inheritance, or polymorphism. C is also statically typed, meaning that, unlike in a dynamic language, we must declare in our C code the types of our variables, function parameters, function return values, and user-defined types. C is also weakly typed in the sense that it is not memory safe. This lack of memory safety is the cost the C programmer pays for control over memory. Unlike in, say, JavaScript, the C programmer can directly read and write individual bytes of memory, and this allows the programmer to potentially make more efficient use of memory, but at the cost of having to manually allocate and deallocate memory. There is no garbage collector in C, so when we create an object, we must keep track of the memory it occupies so that that memory may be reused when we're done with the object. This burden not only complicates code, but also leads to a whole swath of potential bugs. When a C compiler generates machine code, it has a lot of freedom in how it might optimize the code. However, for the sake of interoperation with natively compiled code from other languages, such as assembly, the C language establishes a so-called calling convention, a convention for how functions are invoked in terms of machine instructions. The details, of course, differ for different compilation targets, e.g. the x86 processor calling convention differs from the ARM processor calling convention, but the idea is that within a particular platform, C code can be linked with any non-C code that abides by the same convention. Understand, though, that for languages which do not compile to native machine code, like, say, JavaScript, interop with C code requires much more complicated solutions. Because C compiles to native machine code, gives the programmer control over memory, and can interop quite easily with assembly code, C is very well suited to what we sometimes call systems programming, which refers to writing the low-level code of operating systems and device drivers. The Linux kernel, for example, is written mostly in C. These facets of C also facilitate high-performance code, making C very suitable for performance-sensitive purposes, such as games and media playback. In fact, most high-performance games today are written in C++, which shares these facets of C. Instead of having just one number type, as we do in JavaScript, the C language has several number types, each representing numbers with a different number of bits, and therefore supporting a different range of values. 4 of the most commonly used number types are char, int, float, and double. A char, pronounced by some as char, as in character, is an integer stored as a single byte. A char is so named because it is most commonly used to store an ASCII character. By default, a char is signed, meaning it represents both negative and positive values using 2's complement form, so a signed char can represent the values from -128 to +127. While we can perform arithmetic on chars, our first choice for doing arithmetic is to use ints. An int, short for integer, unlike a char, is stored as multiple bytes. How many bytes exactly depends upon the compiler and the target of compilation. When compiling for a 32-bit processor, an int is most commonly 4 bytes, but when compiling for a 64-bit processor, an int may instead be 8 bytes. In general, the int size corresponds to the so-called word size of the target platform, the size of bytes which is most processor efficient to use on that platform. Understand that C has no exception mechanism, and a primary goal of the language is high performance, so the basic math operations in C, such as addition and subtraction, will trigger overflow silently. For example, when adding 2 int values together, if the result exceeds the range of an int, we get back a value with the most significant bits simply truncated to make the value fit in range of an int. Such results are, of course, not mathematically accurate, but as a C programmer, it is your responsibility to work around such inaccuracies. It turns out that most programming tasks dealing with integers only need full accuracy within a limited range of values that fit comfortably in the smallest size int. If, however, you ever do need full precision math, you can create your own special math functions and data types for that purpose, or more likely simply use an already existing library that does this for you. As for floats and doubles, both are floating point number types, with the only difference being that in the terminology of the IEEE floating point standard, a float is single precision while a double is double precision. Single precision has 23 bits of significand, 8 bits of exponent, and 1 sign bit, totaling 32 bits, while double precision has 52 bits of significand, 11 bits of exponent, and 1 sign bit, totaling 64 bits. At least, these are the sizes prescribed by the C99 standard. Among compilers that don't support C99, the precise sizes of floats and doubles can vary. Because C is a static language, we must declare the type of any variable. When creating a variable, we specify the type before the name. Here, for example, we have two statements declaring variables. The first declares a variable of type int named monkey. The second declares a variable of type float named zebra. Henceforth, when we assign to these variables, we can only assign ints to monkey and floats to zebra. Notice that, like in JavaScript, every statement in C ends with a semicolon. Also, because C is a static language, we must declare the types of a function's parameters and the type returned by the function. The general syntax is first we have the return type, followed by the name, followed by a comma-separated list of the parameters in parens, followed by the body of statements in curly braces. We can insert as much white space between these elements as we like. For instance, we could put spaces between the name and the parens. The only white space that is absolutely required here is between the return type and the name, because of course without any white space between them, the compiler could not distinguish the two. Here are two simple C functions. The first function, named square, takes a single int as argument and returns an int. Its body contains one statement, a return statement returning the value of n times n. The second function, named cube, also takes a single int as argument and returns an int. Its body contains one statement, a return statement returning the value of n passed to square multiplied by n. Again, because C is statically typed, compilation will fail if either of these functions is called with the wrong number or types of argument. So we cannot say invoke cube with a float value anywhere in this code. Compilation will also fail if a return statement's expression doesn't match the function's declared return type. So say it would not be okay if the expression of the return statement in square were to evaluate into a double. Here we have another function foo, which takes 3 arguments, an int and 2 floats, and returns a char. Notice that the parameters are separated by commas. To get type conversions of a value, we have the casting operation. A cast is written as the target type in parens preceding an expression. The cast returns the value of the expression converted into the specific type. The caveat is that some values which we can represent in one data type may of course not be representable in another. So some type conversions can only produce approximate or truncated values. For example, when converting from a float to an int, any fractional component the float might have gets discarded, and the float value may get truncated to fit in the range of an int if it's too large. In other cases, though, the conversion may preserve the precise value. Here, for example, we have an int variable x with the value 35. Assuming the function bar here expects a char argument, we can't pass an int as argument. We can, however, cast the int value of x to a char, and because the value 35 fits within the range of a char, the precise value survives the conversion in this case. If, though, the value of x were, say, 460, the cast to char would require truncating the value to fit in char range. Unlike JavaScript and most other modern languages, C has no Boolean type. Instead, C's condition expressions and Boolean operations treat the number 0 as false and all other number values as true. So, for example, the not operator, the exclamation mark, expects a numeric operand. If the operand is 0, it returns 1, but if the operand is anything other than 0, it returns 0. So, for example, the not operator used on the numeric values 1, 0.6, 3, or negative 6.5, they all return 0, but the not operator used on the numeric values 0 or 0.0 returns 1. Like in JavaScript, each function in C is its own local scope. Unlike JavaScript, functions in C cannot be nested within other functions, but constructs like if and while constitute their own local scopes. So here in this function Roger, the variable z declared within the body of the if only exists in the if's body and not the rest of the function. So these uses of z in the rest of the function trigger compilation errors. To fix this problem, we simply need to move the declaration of z to the outer scope of the function itself, and now it is visible throughout the whole function. You may have noticed that the return type of Roger is void. The void type designates nothing, so this function doesn't return a value, which is why you see no return statements. Here's the Hello World program in C. The first line beginning with a number sign is an include directive, which we'll explain later, but in short this include gives us access to the standard library function printf, which prints string output to the console. The F in printf stands for formatted, the significance of which we'll talk about later. Anyway, our Hello World program consists of just one function, a function main that takes no arguments and returns an int. The linker that converts our code into an executable needs to pick one function to invoke at start of execution, and by default, that function is the one called main. So this main function will be implicitly called when the program starts. Inside main, we invoke printf with the string hello world and then return 0. The reason our main function returns a value at all is that Unix systems expect programs to return a so-called exit code upon completion. What this error code means is entirely up to our program's choosing, but by convention, the exit code 0 generally indicates normal successful completion. Values other than 0 are generally used to represent some kind of fail state. When our program completes, the exit code is received by the other program which runs our program, and what that other program does with the information is entirely up to that other program's choosing. In an earlier video, I discussed the distinction between reference variables and value variables. A reference variable holds the address of a value, whereas a value variable directly holds a value itself. Variables in C are always value variables. Here, for example, this float variable Alex occupies in memory the number of bytes required to store a float value and directly stores any float value assigned to it. C does, however, have a near functional equivalent of reference variables in the form of pointers. A pointer is a data type that represents an address and so effectively can reference a value elsewhere in memory. There isn't just one single data type called pointer, instead there is a pointer type for every other type in the language, e.g. an int pointer type, a double pointer type, and a char pointer type. The idea is that, say, int pointer values represent addresses of int values, double pointer values represent addresses of double values, char pointer values represent addresses of char values, and so forth. To declare a pointer, we use asterisk like a modifier on the base type. This syntax can be very confusing, especially when we introduce some complications later. So for clarity, I'll display asterisks denoting a pointer declaration in orange to distinguish them from other uses of asterisk. This asterisk of a pointer declaration need not be written adjacent to the variable name as we see here. Whitespace after the asterisk is permitted and whitespace before the asterisk is only optional. However, for reasons that will become clear later, this is the preferred style. The reference operator returns a pointer value representing the address of a variable. More accurately, the reference operator works on what the C standard calls L values, which are any expressions which are valid targets of assignment. The L stands for left, as in the left side of an assignment operator. Variables are the most obvious kind of L value, but as we'll see shortly, there are a few other kinds. So the reference operator works on any expression which is a valid target of assignment. Anyway, in this example, we declare an int variable I, an int pointer variable p, and then use the reference operator to assign to p an int pointer value representing the address of I. It's very important to understand that the reference operator used on an int variable produces an int pointer, not any other kind of pointer. If, say, we instead had a char variable c, the reference operator used on C returns a char pointer value, and so this assignment is invalid. We cannot assign a char pointer value to an int pointer variable. An int pointer and a char pointer are two different types, just like an int and a char are different types. However, because all pointers are addresses, and addresses in a single program are ultimately all the same kind of underlying data, a pointer of any type can always be cast to any other kind of pointer. Here we cast the char pointer value to an int pointer, and so the compiler accepts this assignment. As we'll discuss shortly, pointer conversions like this can lead to nasty bugs if you're not careful. The dereference operator returns the value at the address represented by a pointer. The type of the returned value depends upon the type of the pointer, e.g. dereferencing an int pointer returns an int value. Confusingly, the dereference operator is an asterisk. I'll display the dereference operator in green to make it easily distinguishable from other uses of asterisk. Anyway, here we have an int variable I with the value 3, then an int pointer variable p to which we assign the pointer representing the address of I. In the last line, we use the dereference operator to get the int value at the address represented by the pointer p, and then add this int value to 2. So because p represents the address of the variable I, which currently has the value 3, this adds 3 to 2, and so the new value assigned to I is 5. Now, aside from variables, dereferencing expressions are the other primary example of L values. A dereference as the target of an assignment represents a location to which we can assign a value. So here we again have an int variable I and an int pointer variable p holding a pointer value representing the address of I. In the last line, we're assigning the int value 6 to the dereference of p, meaning the value 6 is copied to that address represented by the pointer value. Because p represents the address of I, this assignment does the same thing as if we assigned 6 to I directly. Be clear that the value's type must be the same as the type of the pointer. If p were, say, a float pointer, then the value to assign would have to be a float. Aside from dereferencing pointers, we can also perform addition and subtraction operations on pointers with integers. When we add an integer to a pointer, we get a pointer value of the same type, representing an address that is that number of places above in memory. To explain what I mean by place, it's easiest to just consider an example. Here the reference of I returns an int pointer, and adding 2 to that pointer value returns an int pointer value that represents the address that is 2 ints above in memory. So if our compiler treats ints as 4 bytes, the address represented by this new pointer is the address of I plus 8. We generally don't know the exact addresses of our variables, but supposing that the variable I happens to be located at address, say, FFFF0008, then p would be assigned a pointer representing the address FFFF0010, which is 8 bytes higher. Remember, we're dealing in hex here. Whatever the actual addresses and whatever the size of ints for your particular compiler, the consistent part is that there is space to store 2 ints starting at the original address, going up to but not including the new address. We can also subtract integers from pointers, which produces a pointer representing an address that is lower in memory rather than higher. So again, assuming 4-byte ints and assuming that the variable I happens to be located at address FFFF0008, then p would be assigned a pointer representing the address FFFF0000, which is 8 bytes lower. Once we have a pointer value produced by addition or subtraction, we may dereference it just as we may any other pointer value. So here we can dereference p to get an int value even though p currently points to an address which may not even contain a variable. Regardless, this dereference will read the bytes at the represented address as an int value and copy that int value to the variable I. Likewise, we can assign to the dereference of pointers produced by a pointer arithmetic. This here copies the int value 6 to the bytes located at the address pointed to by p, wherever that may be in memory. It's very important to understand how dangerous pointer arithmetic can be. While our trivial examples here are legal code that will compile, they wouldn't make sense in a real program and could trigger program failure. In these examples, we have no idea what resides at the memory pointed to by the results of our pointer arithmetic, and so it is totally unsafe to either read or write the bytes at those locations. As we'll see shortly, pointer arithmetic should only be used to get pointers that point to addresses which we know have been allocated in our process and for which we know what type of data is there. Not only can we add integers to pointers and subtract integers from pointers, we can also subtract one pointer from another if they are pointers of the same type. Doing so returns an integer expressing the distance between the two pointers in terms of that type. For example, if we have two float pointers that represent addresses 36 bytes apart, well then, assuming 4-byte floats, subtracting the pointer representing the lower address from the other pointer will return 9, because 9 floats fit in the space represented by the addresses of the two float pointers. If we reverse the subtraction, if we subtract the pointer representing the higher address from the other, then we would get -9. You might expect that C would also allow us to add one pointer to another, but this is not the case because adding one memory address to another produces no useful information. The fact that my house is located at street number 3 and yours is located at street number 5 has no logical relationship to the house that might exist at street number 8. In some low-level programming, such as when writing device drivers, situations may arise in which we wish to read or write a specific fixed address. For such scenarios, we can cast an integer to a pointer to get a pointer value representing that specified address. Here, casting a hexadecimal number to a char pointer returns a char pointer representing that specific address. When we then dereference p in the next line, we get back the char value at that address. Again, this is a very dangerous thing to do if you don't know for sure what, if anything, resides at these addresses. What C calls a null pointer is simply a pointer value representing the address 0. C guarantees that address 0 will be left unused, so a null pointer is guaranteed to represent nothing. Normally, we can't assign numbers directly to a pointer, but the number literal 0 is a special case. When you assign the number literal 0 to a pointer, C assigns a null pointer to the target without you having to cast the number to a pointer. Just like with number values, we can compare pointer values with comparison operators. As you would expect, if two pointers represent the same address, they will test equal, and if one pointer represents a higher address in memory than another, it is greater than the other. Also, like number values, pointer values have truth value. A null pointer is considered false, while any non-null pointer is considered true. So, because C always leaves address 0 unused, we know that after assigning the dereference of variable I to p, the pointer held in p will hold a non-null pointer value. Therefore, this if condition will test true, and this not operation will return 0. If instead we assign a null pointer to p, then the same if condition will test false, and this not operation will return 1. Void, as we briefly mentioned earlier, is a special type that represents nothing. A void pointer is a generic pointer type that can substitute for any other kind of pointer without casting. Here we have a void pointer variable Terry and an int pointer variable Ilsa. When we assign Ilsa to Terry or Terry to Ilsa, we can do so without casting. You may recall that we said C is a weakly typed language. Well, here's an example of what that means. Here we have a float variable f, to which we assign the value 98.6. We then have a char pointer variable p, to which we assign the reference of f cast to a char pointer, such that the value of p now represents the address of the first byte of the float variable f. We then increment p by 2, making the value of p represent the address of the third byte of the float. In the last line, we assign 1 to the dereference of p, so the char value 1 is written in the third byte of the float. Effectively, we have arbitrarily overwritten a portion of our float. In a strongly typed language, I should only be able to manipulate a piece of data with operations expressly defined for that type, but here we're using pointers to do an end run around the normal float operations. Arbitrarily munging a random byte of a float makes no sense as far as the float type is defined, but C lets us do this because it is weakly typed. In C, it's the programmer's responsibility to preserve the sanctity of the data types, not the language's responsibility. If I haven't made it clear yet, we shouldn't presume anything about the relative positions of variables in memory. If we have a contiguous chunk of memory, on the other hand, then it can make sense to play around with pointer arithmetic. So how do we get contiguous chunks of memory? There are two ways, by allocating memory on the heap or by creating arrays on the stack. We'll look first at allocating memory on the heap. Recall from earlier videos that the heap space of a process starts out unallocated, meaning that the OS hasn't actually mapped the process's virtual addresses to actual physical memory, and so using those unallocated addresses triggers a hardware exception. To use heap space, a process must explicitly request that the OS allocate a chunk with a system call. In the system call, the process specifies how big the chunk should be, and the OS responds either with the starting address of a newly allocated chunk of that size, or with an error if the request cannot be fulfilled. Once a process no longer needs a chunk of heap space, the process should tell the operating system to deallocate that chunk with another system call to which is passed the chunk's starting address as argument. If a process hangs on to allocated chunks it doesn't need, the process wastes memory and risks running out, especially if the process allocates many chunks over a lengthy running time. A server program, for example, is typically kept running for many days if not months or years, and so failing to properly deallocate unused memory will very likely lead to the process exhausting available memory at some point. In garbage-collected languages, the language itself does the allocating and deallocating for us, but in C, that job is left to the programmer. The C standard library contains the functions malloc and free, which invoke the allocate and deallocate system calls respectively. Malloc, short for memory allocation, takes a number of bytes to allocate as argument and returns a void pointer. So here the void pointer returned by the first call to malloc is assigned to void pointer variable v, and the void pointer returned by the second call to malloc is assigned to float pointer f. We then do whatever we want with these two heap chunks represented by these pointers, but once we're done with them, we should deallocate these chunks by passing the pointers to free. The free function expects a void pointer as argument, so we can pass f to free without having to cast. When allocating memory, we very often want chunks sufficient to store a particular number of values of a particular type. For example, I might want to store 100 ints. If I know that my target platform uses 4-byte ints, I could then simply allocate 400 bytes. But what if I intend to compile my code for multiple platforms? The solution to this problem is the sizeof operator, which returns the size in bytes of a specified type. Sizeof is a strange operator in two regards. First, it is written as a word rather than a symbol. Second, sizeof takes a type as operand, not an expression. Anyway, here are three examples. The first returns the number of bytes occupied by an int, the second returns the number of bytes occupied by a double, and the third returns the number of bytes occupied by a float pointer. Notice that the float pointer type requires parens because otherwise the asterisk wouldn't be considered part of the type. For consistency and clarity, some programmers like to always surround the type in parentheses in the style of a function call, even though sizeof is not a function. So here we put sizeof to practical use. We invoke malloc with the argument 7 multiplied by the sizeof int. So say, assuming 4-byte ints, malloc here returns a chunk that is 28 bytes. If we then assign 12 to the dereference of p plus 0, we are writing the int value 12 into the first 4 bytes of the chunk. Assigning 13 to the dereference of p plus 1 writes the int value 13 into the second 4 bytes of the chunk, and then assigning 14 to the dereference of p plus 6 writes the int value 14 into the last 4 bytes of the chunk. If we compile and run this code on a platform in which ints are some different size, it will still work as intended. The allocated chunk will always be the right size to fit 7 ints. Remember that the memory allocation system call is just a request, not an order, and so sometimes the OS will refuse the allocation, such as when the system has no more memory to give. Therefore, in practice, we should always check the result of malloc for a null pointer, the value returned when the allocation request is refused. Here, for example, before using the allocated memory return to p, we first check if p is null and branch accordingly. In the branch where allocation fails, we may simply have to abort our program. In the branch where the allocation succeeds, we do what we want with the memory chunk, but then must remember to deallocate the chunk when we no longer need it. What C calls an array is a chunk of memory allocated on the stack rather than the heap. Because an array is stack allocated as part of its containing function stack frame, it is automatically deallocated by the language. When execution leaves the scope in which an array is allocated, the memory occupied by the array should be considered deallocated, and so any pointer values representing addresses in bounds of the array should no longer be used. Accessing the memory of an out-of-scope array won't always trigger a hardware exception, but accessing out-of-scope memory should always be considered unsafe and illogical. Creation of an array looks like a variable declaration in which the variable name is suffixed with square brackets containing a size in terms of the type. The name of the array itself is not really a variable, but rather a pointer value representing the first byte of the array. Otherwise, array names are like pointer variables in all respects, except you may not assign them new values. So in these two examples, Jack is a float pointer value representing the address of the first byte of an array that is the size of 8 floats, and Jill is a char pointer value representing the address of the first byte of an array that is the size of 200 chars. In this code, we have an int array I and a char array C. Because the name I is an int pointer value, we can assign it to the int pointer variable p. We can also dereference array names just like a normal pointer. Here, when we assign -6 to the dereference of I, we are writing the int value -6 at the start of the array. When we assign 8 to the dereference of I plus 1, we're writing the int value 8 at the address which is one int-sized chunk up in memory from the start of the array I. In the last line, when we assign the char value 5 to the dereference of C plus 7, we're writing the char value 5 at the address which is 7 char-sized chunks up in memory from the start of the array C. Note that we have to cast the number literal 5 to char, because the number literal is an int and we can't assign an int to a char L value. Now let's look at a somewhat realistic example of something we might do with arrays and heap allocations. Here's a function sum that takes an int pointer nums and an int n as argument. Nums is expected to point to the start of a contiguous block of ints, meanwhile n is expected to denote the number of ints in the block. The function then loops from 0 up to, but not including n, and in each iteration we add to sum the dereference of nums plus our counter I. At the end of the loop, sum will hold the sum of every int in the block. So here's one example of how we might call the sum function. Say we create an array of 3 ints called a, and then we populate the ints of the array with various int values. If we then pass the array name a and 3 to sum, it will return the sum of all those ints. Because the sum function expects an int pointer, we just as well could pass it a block of heap allocated memory. Here, assuming the call to malloc doesn't return a null pointer, the pointer p represents a block the size of 3 ints, and we can pass this block to sum. If you're wondering why we might ever use blocks of heap memory rather than arrays, which seem more convenient, well, consider the problem with this function. This function Fred returns a char pointer, and the body simply creates and returns a pointer representing the start of the char array. While legal, what this function does is very dangerous because the array is allocated in the stack frame of the call to Fred, and so goes out of scope once the call returns. So what the caller of Fred gets back is a pointer to memory that is unsafe to use because it will likely get overwritten by the frames of subsequent function calls, and even if that doesn't happen, the process's stack boundary might move such that accessing the memory of the array will trigger a memory access violation. All around, using stack allocated memory that goes out of scope is just a bad scene. In this alternative version of Fred, we heap allocate a block of memory instead of creating an array. Because this block lives on the heap, it is safe to use until we explicitly deallocate it. Notice that it is the caller of Fred's responsibility to test whether Fred returns a non-null pointer and to free the block. Now that we've introduced arrays and heap allocation, we can talk about strings. In truth, C has no actual string type. When you see a string literal in double quotes, the expression is actually a char pointer value that represents the address of where the characters of the string are actually stored. The characters of a string literal are encoded as ASCII and stored in the process's text section, aka the unmodified part of your process's memory where the code itself is stored. The end of the string is denoted by a null byte, a byte that is all 0 bits. So here we have a string literal with the characters A, B, C. This text is stored as 4 contiguous bytes in the process's text section, and the string literal is a char pointer value representing the address of the first of these 4 bytes. So here, when we assign the string to char pointer s and then dereference s plus 1, we get back the char value residing in the second byte of the string, which will be 98, the ASCII value for lowercase b. The C standard library contains a number of functions for working with strings in this format. The strlen function, for instance, short for string length, returns the number of characters in a string up to but not including the null byte that terminates it. Here we pass strlen the character pointer s, and strlen will read the bytes at that address until it encounters a null byte and returns the count of bytes read, not including the null byte. So the int variable I will be assigned to the value 3. C has no built-in support for strings in other formats, but if you want to work with, say, Unicode strings, you can do so by storing their bytes in arrays and heap allocated blocks. Just keep in mind that these standard library string functions will only correctly handle ASCII encoded characters terminated by null bytes. When using Unicode strings, you'll need Unicode-specific functions to provide the equivalent functionality on those strings. C is not object-oriented and so has no concept of classes, but it does have user-defined data types called structures. Unlike a class, a C structure has no notion of methods. A structure is just pure data. To declare a structure type, we use the reserved word struct, followed by a name, followed by a list of members in curly braces. Having declared this struct type, we can then create a variable of this type just as if we were creating a variable of a built-in type, except the type name is preceded by the reserved word struct. In fact, it's easiest to think of the word struct as if it's part of the type name. Once we have a variable of a struct type, we can access the individual members that make up the struct with the dot operator. So here, for example, we declare a type called struct cat with 2 members, a char pointer name and an int age. We then create a struct cat variable mittens and then assign its name member the char pointer value represented by the string mittens, and then assign its age member the int value 5. We can assign one struct instance to another as we do here, assigning mittens to Fluffy. This copies the value of every member of mittens to the corresponding member of Fluffy. We can also create struct pointers as we can with any other type. Here we assign a struct cat pointer p and assign it the reference of Fluffy, so p now holds a pointer representing the address of the struct cat variable Fluffy. Somewhat surprisingly, we cannot compare struct values with the equality operators, so this expression is illegal. If you want to compare the corresponding members of two struct values, you have to compare them individually. Here we use malloc to allocate a block the size of 8 struct cats, and we assign the result of malloc to a struct cat pointer. We then can retrieve the individual cats of this block using pointer arithmetic and the dereference operator, and once we have an individual cat instance value, we can assign its members with the dot operator. So here we assign the string Oscar to the name member of the first cat, the string Kitty to the name member of the second cat, and the number 4 to the age member of the last cat. If we want a stack allocated block of cats, we can create an array instead of using malloc. We then use the array in the same fashion, but just keep in mind that the block of memory only exists for the duration of the local scope. So far, we've created pointers and arrays out of our base types, and now also the custom struct types which we can create. But the general rule in C is that we can create pointers and arrays of any type, including other pointers and arrays. So we can have pointers to pointers, pointers to arrays, arrays of pointers, arrays of arrays, pointers to pointers to pointers, arrays of pointers to arrays, ad infinitum. For these complex types, a key thing to understand is that arrays of different sizes are considered different types. So say an array of 5 ints is not the same type as an array of 6 ints. So say when we create a pointer to an array of 5 ints, that is a different type of pointer than a pointer to an array of 6 ints. Here's a more elaborate example of a complex type. Because there exists in C an int type, we can also create arrays of int. For example, we can have an array of 12 ints type. And because that's its own type, we can create an array of that type. So we can have an array of 4 arrays of 12 ints type. And because that's its own type, we can create a pointer to that type, a pointer to an array of 4 arrays of 12 ints. And because that's its own type, we can create a pointer to that type, a pointer to pointers to arrays of 4 arrays of 12 ints. And because that's its own type, we can create an array of that type, so we can have an array of 7 pointers to arrays of 4 arrays of 12 ints. Again, be clear that arrays of different sizes are different types. So here we have 3 pointer types which all point to arrays of ints, but because the arrays are of different sizes, these are 3 separate types. Now, you're probably trying to picture what these data types look like in memory. Well, pointers are the easy case. A pointer of any type always represents just a single address. For example, a pointer that points to an individual char is an address, a pointer that points to a pointer to a char is also an address, and likewise a pointer that points to an array of arrays is also just an individual address. As for arrays, an array of n x's is a contiguous block of n x's. So an array of 7 doubles is a contiguous block that fits 7 doubles. An array of 15 pointers to chars is a contiguous block that fits 15 pointers to chars. An array of 4 arrays of 12 ints is a contiguous block that fits 4 arrays of 12 ints, and each array of 12 ints is in turn a contiguous block that fits 12 ints. For illustration, here's an array of 4 arrays of 3 chars. The whole block is made up of 4 blocks, each of which is made up of 3 chars. Here's an array of 2 pointers to arrays of 4 arrays of 12 ints. What we have in memory is simply 2 pointers. The pointers point to arrays of arrays, but the pointers themselves, as always, are merely addresses. Here we have an array of 2 arrays of 3 pointers to arrays of 12 ints. Again, reading left to right, as soon as we're talking about a pointer, we're talking about just a single address, regardless of the type to which the pointer points. One thing that makes these complex types very confusing is that C programmers often use the words pointer and array as modifying adjectives rather than as nouns, and this ends up reversing the order of the components when we state a type. For example, instead of saying an array of 12 ints, we could say an int array sized 12. Even more confusing, we generally leave the array sizes unstated, so we would more commonly just say int array. The more complex our array and pointer types, the more confusion this creates. Instead of saying an array of 4 arrays of 12 ints, we commonly say an int array. And instead of saying a pointer to an array of 4 arrays of 12 ints, we commonly say int array pointer. Because it's awkward to include the array sizes in this way of expressing types, I find it less clear even though it is less verbose. What you absolutely shouldn't do, however, is mix these 2 ways of expressing types. For example, instead of saying a pointer to an array of 4 arrays of 12 ints, or instead of saying an int array pointer, which is equivalent, it would be valid English to say a pointer to an int array, or say a pointer to an array of int arrays. But expressing types this way is horribly confusing. Sadly, many programmers use this manner of expressing types quite commonly. Just watch out for it and try avoid using it yourself. If you're ever confused about a complex pointer or array type, put the component types in a consistent order as I've demonstrated. Okay, so the next question is, what syntax do we use to create these complex types? Well, before getting to this syntax, consider the nature of unary operators. For a moment, imagine if, in the C language, $, number sign, and the @ sign were all unary operators. They aren't, but just imagine this were the case. This use of the three operators on foo, for example here, would be applied from right to left. Now imagine if the @ sign were postfix rather than prefix, meaning it would be written after its operand rather than before. Now the order of operations depends upon the order of precedence. If the @ sign had highest precedence, then this would be the evaluation order. If though the number sign had highest precedence and the @ sign had second highest, this would be the evaluation order. And if the @ sign had lowest precedence, then this would be the order. So the point is that when both prefix and postfix operators are involved, we have to be concerned about the respective precedence. Now, what do operators have to do with declarations? Normally, we think of operations only existing in expressions, and a declaration is not an expression. Well, for some strange reason, the C language decided that declaration syntax should mirror expressions, and so square brackets in a declaration act like a postfix operator, and asterisk in a declaration acts like a prefix operator, with the square brackets having higher precedence than asterisk. And just like in an actual expression, we can use parens to subvert this precedence. So in this declaration of an array, you should think of the square brackets as an operator on the name foo, but which has the effect of modifying the base type int to be an array of the size specified in the square brackets. So this is a declaration of an array of 12 ints. In this next declaration, we have another pair of square brackets containing the number 4. Because this pair is closer to the pseudo-operand foo, this is firstly an array of 4. So this is an array of 4 arrays of 12 ints. In this next declaration, we've added an asterisk and enclosed it in parentheses around foo. Without the parentheses, the square brackets would have higher precedence, but with the parentheses, the asterisk is applied first, so this is a pointer to arrays of 4 arrays of 12 ints. Lastly, we've added an asterisk outside the parens and moved the first square brackets to be inside the parens. So because square brackets have a higher precedence than asterisk looking inside the parens, this is an array of 4 pointers, and then looking outside the parens, these pointers point to arrays of 12 pointers to ints. So the general pattern of declaration syntax is that we start with a name and read the modifiers inside out, going by the order of precedence, except where parens intervene. Now, as for actually using these complex types, we need to cover a few rules. First, referencing a pointer type variable will return a pointer to that type. Here, we assign the reference of int variable I to pointer to int variable Jason, and then in turn, assign the reference of Jason to pointer to int variable Amanda. So the reference of Jason returns a pointer to int value. When dereferencing a pointer to x, we get back a pointer to x value. So here when we dereference Amanda, which is a pointer to int, we get back a pointer to int. If we use a dereference operator on Amanda twice, then we're dereferencing the pointer to int value returned by the dereference of Amanda, and so we get back a plain int value. As previously discussed, an array name is really a pointer value. Notice that I said pointer value and not variable because we cannot assign to array names. Here we can assign the array name foo to an int pointer variable, but we cannot assign the int pointer variable back to the array name. For this array of 7 pointers to ints, the array name is itself a pointer to pointers to ints. For this array of 7 arrays of 4 ints, the array name is itself a pointer to arrays of 4 ints. Normally, we can only use the reference operator on L values, which, as we discussed earlier, are valid targets of assignment. A special exception, though, is made for array names. If you reference the name of an array of n x's, you get back a pointer to an array of n x's. So here we can assign the reference of foo to this pointer to arrays of 7 ints. Again, as we've said repeatedly, the size of an array is an inherent part of its type, so this example fails compilation. A pointer to arrays of 7 ints value cannot be assigned to a pointer to arrays of 9 ints variable. Now, here's the rule that's most surprising. Normally when we dereference a pointer to x, we get back the x value to which the pointer pointed. The exception is with pointers to arrays. An array is not an actual kind of value, so dereferencing a pointer to an array can't possibly return an array value. There's just no such thing. Instead, dereferencing a pointer to an array of n x's will return a pointer to x. So here, dereferencing this pointer to arrays of 7 ints variable bar returns a pointer to int, which we can assign to the pointer to int variable p. As we discussed earlier, a void pointer is a generic kind of pointer, such that we can assign any kind of pointer to a void pointer without having to use a cast. Just like with the other pointers, we can create pointers to these pointers, so we can have a pointer to void. So here we have a void pointer variable Terry and a void pointer variable Dara, and we assign the reference of Terry to Dara. Because again, pointers of all types are just addresses, we can convert pointers of any type to pointers of any other type with a cast. But again, the special thing about void pointers of any degree is that we needn't cast other pointer types to assign the void pointer variables. So here we can assign Dara to Terry and vice versa without any casting, even though void pointer and void pointer are different types. The same is not true of non-void pointers, such as here when we must cast both Terry and Dara when we assign them to int pointer variable Ilsa. When going the other way, when assigning int pointer Ilsa to Dara and Terry, we don't need to cast, but the assignment of Ilsa to void pointer Dara will trigger a compiler warning unless we make the cast explicit. For some reason, the C99 standard decided that implicit casts to void pointers are okay, but implicit casts to void pointers are too error-prone to pass without a warning. It's very important in C to distinguish between what the language calls definitions and what it calls declarations. The distinction is quite confusing for 3 reasons. First, the choice of terms is totally arbitrary. It would have been just as logical if the 2 terms swapped meanings. Second, all definitions serve double duty as declarations, but a declaration is not necessarily a definition. Third, in common parlance, the terms are used very sloppily. In particular, it is very common to say variable declaration when we should say variable definition. In fact, I made the same mistake in earlier parts of this video. In any case, the distinction between definition and declaration is that a definition actually creates a variable or function, but a declaration merely states the type associated with a name. For example, a function definition specifies a function's name, parameter names and types, the return type, and provides a body in curly braces because the definition actually creates a function. A function declaration, on the other hand, specifies the name, the parameter types, and the return type, but not the parameter names or a body. You actually can specify parameter names in a function declaration, but they are ignored by the compiler. So here, for example, we have a function definition that creates a function foo, which returns a void and takes 2 parameters, an int called x and a float called y, and of course, to create a function, we must provide a body. In contrast, the declaration of this same function omits the body, and so instead ends with a semicolon. An important difference between definitions and declarations is that a variable or function may only be defined once, but may be declared as many times as needed. So the next question is, why do we need declarations? Well, to generate code that uses a name, the compiler needs to know the type associated with that name, and declarations provide this information. In many cases, the definition of a variable or function suffices as its only needed declaration, but there are 2 situations where this is not the case. First, the code of a C program is generally split into separate source files that are compiled separately. If code in one source file needs to use a name defined in another source file, that name must be declared in the first source file. Second, C compilers strictly read source code files top to bottom, such that declarations of a name must precede any use of that name. In many cases, you could rearrange the order of your definitions within a source file to satisfy this requirement, but this won't work if the file includes recursive functions. Besides, having to put our definitions in a particular order is bothersome, so a common practice is to put declarations of every function at the top of the file whether they are strictly needed or not. So consider a few examples. Assuming this shows the entirety of a source file, this call to bar triggers a compile error because no declaration of bar precedes the call. We can fix this by simply switching the order of the definitions. Because the definition of bar also counts as a declaration of bar, the compiler sees a declaration of bar before the call to bar. If we don't feel like reordering our definitions, a bothersome thing to do, we could simply add a declaration of bar in the function where it is called. As long as this declaration precedes any call to bar in the function, the compiler is happy. Putting ad hoc function declarations in your code like this is not a very common thing to do, however. The more common and general solution is to put a declaration of every defined function at the top of the source file. This way we can put our function definitions in any order without upsetting the compiler. Here's how you should actually think about the function declaration syntax. Just like asterisk is a modifier that makes a type a pointer, and just like square brackets are a modifier that makes a type an array, the parentheses, which contain a list of parameters, are a modifier which makes a type a function. This is confusing because parens are also used to subvert order of precedence. The distinction is that the parens of a parameter list are a postfix operator just like the square brackets. These parens come after what they modify rather than surround what they modify. Also, like the square brackets, these parens have a higher precedence than asterisk. Here we have a declaration of a function called foo that takes two parameters and returns an int. As we just discussed, the way to read the syntax is to read the modifiers on the name in order of precedence. The parameter list is the only modifier, so foo is a function taking an int and char and returning an int. In the second example, the empty parameter list has higher precedence than asterisk, so foo is a function taking no arguments and returning a pointer to int. In this third example, the empty parameter list again has higher precedence than asterisk, and thanks to the surrounding parens, the asterisk modifier is applied before the square brackets, and so this is a function taking no arguments and returning a pointer to an array of 7 ints. Be clear that these three examples are declarations but not definitions. Each declares a function taking some set of parameters and returning some type. It's also important to understand that not all possible combinations of these modifiers are valid. Reading the modifiers inside out as usual, this example declares a function foo that takes no arguments and returns an array of 7 pointers to int. But this declaration is invalid because arrays are not values like ints or pointers, and so a function may not return an array. Again, reading the modifiers inside out, this example declares an array of functions taking no arguments and returning pointers to ints, but this declaration is also invalid because there's no such thing as an array of functions. What we can create, however, are pointers to functions. Here, reading inside out, foo is a pointer to a function taking no arguments and returning an int. And because we can create arrays of pointers, we can create arrays of pointers to functions. Here, foo is an array of 6 pointers to a function taking no arguments and returning int. But again, there's no such thing as an array of functions, and so we can't create pointers to arrays of functions. So you're probably wondering, what is a pointer to a function, beyond of course just another memory address? Well, it turns out that function names are always actually function pointer values. So when we invoke functions in C, we are actually invoking function pointers. Much like in, say, JavaScript, where you can invoke as a function any expression which evaluates into a function object, in C, you can invoke as a function any expression which evaluates into a function pointer. Here, for example, if we have some defined function foo which takes no arguments and returns an int, then we can assign foo to a variable p, which is a pointer to a function taking no arguments and returning foo. We then can invoke the function via the variable p, just as we could via the function name itself. Be clear that the argument and return types of a function are integral to the pointer's type, so if the p variable were a pointer to a function taking a char argument and returning int, it would not be a valid assignment target for foo. Like an array name, a function name is a value, not a variable. This means that function names cannot be reassigned. Also, referencing a pointer to a function does not return a pointer to a function, as you might expect, but rather simply returns the same pointer value. So here, assigning the reference of the function name foo to p does the same thing as simply assigning the name foo itself to p. To be honest, I'm not sure why referencing a function name doesn't simply trigger a compilation error. It's not as if referencing function names does something useful. Another strange thing about function pointers is that, like with arrays, there's no such thing as a function value, so dereferencing a function pointer cannot return a function. Instead, dereferencing a function pointer value simply returns the same function pointer value. Here, the dereference of the function name foo returns the same function pointer value represented by the name. When we dereference p, we get the same function pointer value, which we can then invoke like any other function pointer value. Like with referencing function names, I'm not sure why dereferencing function pointers is allowed, because it doesn't do anything useful. Now, it is possible to get a function pointer value by referencing a function pointer variable. Here, the reference of variable p returns a function pointer. To invoke functions, however, we may only use function pointers themselves, not function pointers. So we cannot invoke function pointer variable p2, but we can invoke the dereference of p2. Note that parens around the dereference of p2 here are very necessary, because without them the argument list parens would have higher precedence, and so this expression would be the dereference of the value returned by a call to p2. which is not only the wrong syntax, but would be an invalid operation because we can't invoke p2 as a function. In a few contexts, we need to specify pointer types without having any name to modify. Here, to cast the value of this variable foo into an int pointer, there is no name for the asterisks to modify. In the next example, to cast a variable foo into a pointer to an array of 8 chars, we need to surround the asterisk in parentheses to subvert the precedence. Otherwise, the cast type specified would be an array of 8 char pointers, which is not only the wrong type, but would make this cast totally invalid because you can't cast to arrays. Arrays are not a kind of value. In this last example, rather than casting, we're declaring a function bar. This declaration states that bar takes as argument a pointer to a function which takes no arguments and returns int, while bar itself returns float. Note that the parameter type declaration requires parentheses around the asterisk to subvert the higher precedence of the empty parameter list parens. In an earlier video, we discussed how natively compiled languages typically go through a two-step process. First, each source file is separately compiled into object code files, and then these object code files get combined into a single executable by a program called a linker. Here's a simple example of how this works in C. Say we have two source files, one called main.c and another called foo.c. Both of these files are compiled separately, and so when compiling main.c, the compiler has no knowledge about how the function foo is defined. However, main.c includes a declaration, a function foo with the same parameter types and return type, and so the compiler can generate appropriate machine code for invoking foo. What's missing though is an actual address for execution to jump to when invoking foo. That gets filled in by the linker. The linker takes the two object files separately compiled from these two source files and from them produces a single executable. In the executable, there's an actual address for execution to jump to when invoking foo. By default, the executable produced by the linker will invoke the function called main to kick off execution of the program. So our compiled and linked program here will invoke main and end when main returns. Understand that C has no notion of namespacing. When the linker matches names from separate object files together, it does so in one global namespace. For example, the linker assumes that the function foo defined in one object file refers to the same function foo invoked in other object files because there is only one global namespace across all object files. This lack of namespaces is a holdover from an earlier era of programming, but C programmers work around this deficiency with a simple convention. A library written in C, by convention, prefixes the names of everything it defines with an initialism or abbreviation of the library's name. The OpenGL library, for example, prefixes the names of what it defines with lowercase gl. While this prefixing convention adds clutter to C code, many C programmers insist they like it because it means that every name clearly states the library from which it comes. In the event of a name collision, such as when using two libraries that define something of the same name, you'll have to tell the linker how you wish to resolve the conflict.